Greetings, everyone. And today is the third webinar in the Tangent series. The topic is transport network optimization and arbitration models. So, considering the topic, before we start the webinar, we just like to go through some logistical aspects during the duration. What we will do is the meeting will be recorded for publishing online and for the internal purposes. So therefore, please raise your digital hand if you wish to speak and mute yourself while you're not speaking. And also be aware that you might be visible on the screen while the recording is ongoing. And during the webinar, we'll also have a Q&A session. So for the Q&A session, if you can see on the top of the MS Teams, there's a Q&A icon. And there you can always raise your questions in case you have any, and you all can already see my message there. And during the presentation, if you have any particular comments or feedback, you can always use the chat for your immediate feedback on the ongoing presentations. So, considering Tangent, it is a European Union Horizon 2020 research and innovation project, and it basically aims to develop new complementary tools for optimizing traffic operations in a coordinated and dynamic way. The cities which are participating are the project aims to help the cities achieve a 10% reduction in travel time and reduction in CO2 emissions, accidents, and also, but at the same time, increase the use of public transport. The consortium and the partners represent 7 European countries, and these range from Belgium, Germany, Greece, Italy, Netherlands to Spain and the United Kingdoms. The participating cities in Tangent for case studies are Lisbon in Portugal, Rennes in France, Great Manchester in United Kingdom, and Athens in Greece. The aim for the webinar series is basically it's part of the work package where we focus on multi-actor cooperation models and policies, and we try to steer the effective knowledge exchange between different stakeholders and partners and experts in the thematic discussions, and also for the future market uptake of the project's results. How does the agenda look like? So we'll keep it strict to 1 hour timeline where first, as currently we're going through the welcome and introduction. And following this, I will share a poll for a Mentimeter, which you'll get in the next slide, in the upcoming slides. At the same time, we'll have 2 speakers who will present on the transport network optimization problems and techniques. That is by Dr. Arka Ghosh from Dovesto, and development of arbitration models, which is by Marius from NTUA Athens. And following this, we will always have 5 minutes of Q&A after each presentation. And after all the 2 presentations, we'll have a poll and concluding remarks where we'll also approach to have further engagement in the Tangent webinar series and through the Tangent forum on the Mobility Academy. Those information we will share towards the end, but also in between the presentations as they're going on. So, considering the 2 speakers of our webinar, we have Dr. Akka Ghosh from Dovesto, and he's a postdoctoral research associate at the Dovesto Tech Faculty of Engineering and University of Dovesto Bilbao, Spain. He holds a PhD in computer science and technology with a focus on optimization theory and machine learning. He has previously worked as a research associate in optimization theory at Victoria University of Wellington, New Zealand, and in Indian Statistical Institute, Kolkata, India. And for the second speaker, we have Marius Georgopoulos. He is a civil and transportation engineer and a researcher at Department of Transportation Planning and Engineering of the National Technical University of Athens. He holds engineering degrees in civil and transportation engineering from NTUA and École Nationale des Ponts at ENPC, and also a master's degree in environmental economics from ENPC. And prior to joining NTUA, he worked at the World Bank and also in Ile de France, Mobilités in Paris, France. he's pursuing his research dissertation on which is titled as Cooperative Decision Making Models for Urban Road Networks under the supervision of Professor Elling. So before we begin with the presentation, I will like to draw your attention to the first poll. So if you can look at the screen, I will share the Mentimeter just in a second. Just let me share the screen. Okay. So if you can see the screens, you can give a thumbs up on the Mentimeter. There's an instruction where we have the codes for the Mentimeter for the first poll. Perfect. So we'll just wait for maybe a few more seconds before I go to the next page, and then you will get the question for the first poll. All right. So the first question, the first poll it addresses is, are you familiar with the traffic network optimization and arbitration approaches for cities? If no, how do you interpret these terms? And if yes, please do mention of any approaches that you're familiar with. You can start typing your responses. Just to remind you, you can join menti.com and use the code 23190755. And once you enter your responses, we'll be able to see your results. Okay. Still waiting for some responses. Okay, we have 2 responses. So interpreting these terms as travel distance, less travel problems, reducing the travel time. Okay, I think these are some of the indicators which we are going towards the traffic network optimization. And also, if you are familiar with any arbitration models or arbitration approaches, that will also be a nice way of looking forward to. Cost function. No, okay. So not everyone is familiar with traffic network optimization and arbitration. So I think that's perfect because that's how we'll approach this webinar, and we'll have the presentations focusing on these 2 topics. Less travel problems, decision making, dynamic traffic lights, cost function, management of congestion, arbitration to select criteria, social benefits, travel time. Okay. We'll wait for 30 more seconds or 10 more seconds, 20 more seconds, and then we'll start with the presentation after this. Okay. So following these responses, we'll keep that in mind. And going forward, I would like to allow or present Dr. Arka to present this first presentation. And if you can share your slides or you can share your screen, that would be perfect.
Thank you, Laksha. I will share my screen.
Yeah.
1 second, please.
Yeah.
Okay. Thank you, Laksha. Good afternoon, everybody. So today we will discuss about different modalities of optimization problems applied to transport network management. I am Arka and I am from University of Deusto, as Lexa has already introduced me. So without any time, we go to the next slide. So in recent times, generation of traffic policy and response plans are getting harder and harder because the transport itself has become multimodal, means there are multiple modalities of travels present, as well as there are other players like multiple stakeholders are also involved in a transport network management. So public authorities must orchestrate both current and future transport modes to manage all these different modes of transport and different stakeholders in a useful and fruitful manner. Higher complexity of this multimodal transport network management is growing day by day, and there are multiple new tools are coming into the play every day. Now, the approach that we have taken is to use computer or optimized design to generate transport policies and interventions to aid the traffic managers in a better and fruitful traffic management. All the methods that we have studied are based on artificial intelligence and transport modeling consensus written mechanism. We will be focusing on two main case studies for the optimization problem. First one is the integration of demand responsive transport and transit modes, and the second one is synchronization of public transport and traffic control. Now, for integration of demand responsive transport and transit modes, the optimization, the term itself in a layman's word is like if you have multiple options to do a task, you choose the best possible option that maximizes your gain. That's the simple definition of optimization. Now, for this particular problem, just imagine that if you want to go to a point A to point B, where point A and point B might not be well connected using public transport lines. That means you might not have a bus stop just outside your apartment, and you might have to walk for a couple of minutes or take another mode of transport to go there. And same for your drop off location. Now, one option is to take a private car or your own car to go from your origin to the destination. But another option is also is to do this kind of demand responsive transport or synchronization, where first you decide where first you decide that where to go, and then based on a optimization method, the algorithm matches you to your nearest public transport stop for both of the cases. So if you are starting from your home, then the algorithm suggests a public transport stop near to your house, and then arrange a DRT service from your house to that particular public transport stop, and then again does the same thing for the last mile. So this problem is known as first mile and last mile problem, where first mile is the synchronization between your house to the nearest public transport stop, and the last mile is that the public transport drop to your destination. So here we try to tackle this problem by means of vehicle routing problem with time windows. So we have used this computer generated design optimization algorithms to determine the optimal or near optimal DRT fleet and operation routes for best first and last mile service. The performance indicators that we have considered are percentage of demand served, means if in a time window, let's say from 8 to 9 a.m. in a day, if we receive 100 requests of such things, how many of them are fruitfully resolved? Like how many of them were successfully resolved is known as the percentage of demand served. And the total emission produced by the DRT fleet means in order to serve these demands, we must have a fleet of cars ready, like the DRT fleet. So the total emission by the fleet, the operation cost of the DRT service. So for this first and last mile DRT service, what will be the total cost for management and maintaining those things, and the average travel time for the passenger itself. So this is the most important point from the passenger's perspective, because this is the time required to go from your house to your nearest public transport stop, then the public transport travel time, and then again from the public transport drop to your destination. So we have tested this methodology uh, for Athens case study, where as per the map you can see there are two regions, one's in so in the red boundary and another in the blue boundary. So the connection between this blue area and the red area is tested for this purpose, and there are 200 total trip requests. 200 total trip requests means there are originally 100 requests, and as I have already discussed, each request is divided into two parts, first mile and last mile. This 100 requests becomes 200 total requests, and the request locations are randomly generated within the specified area. Means this within this blue area, they are randomly generated, and the start and departure time windows are also generated randomly from 8 a.m. to 2 p.m. in the morning part. And this is the normal formulation for the departure time window and arrival time window calculation, where the normal travel time is around 30 to 35 minutes for one thing, and another is 105 minutes. Now we have tested this setting with tested this problem with two different settings. One with 6 vehicle fleet, that means the DRT fleet has 6 total number of vehicles, and another one is 16 vehicles. So first I will present the result with 6 vehicles, and then I will go to the result with 16 vehicle presentation. Now, as we have already discussed, the performance key indicators that we considered, one of them is operational cost for the DRT fleet. For here, you can see the total operational cost of DRT fleet is 1,332 euro. The demand served by DRT service for first mile and last mile, both cases, is 28%. That means 56 out of 200 requests were completely satisfied. Now demand served for only first mile was 57%, and demand served for DRT service only for the last mile, it should be last mile, was 57.5%, where it was around 115 requests among these 200 total one. The DRT fleet emissions are listed as below, where we have generated like 64.5 gram of carbon monoxide, 150 kilogram of carbon dioxide, 151 gram of nitrogen dioxide, and 671 gram of NOx based pollutants, and 21.3 grams of PM2.5 pollutants. The average passenger travel time, means considering the public transport time as well as the DRT time, is 76.5 minutes for average passenger, for each passenger in a term. And if the passenger was only taking public transport without the DRT service, the passenger travel time was 88.5 minutes. So you can see there is a difference between taking this synchronization service and taking this standalone public transport service. Now we are discussing the results with 16 vehicle fleet. So this is a larger fleet structure. So that for that reason you can also see that the operational cost has gone up because the number of vehicles are much higher, but also the demand served is also much higher. So you can see the demand served by the DRT service for first mile as well as last mile has gone up to 98%. So now 196 requests out of 200 were satisfied fully. And for the same, for the first, only for the first mile is 100 for 98%, for 196 out of 200 requests, and for last mile it was 100%, like all the requests were satisfied. The DRT fleet emissions are definitely higher than the previous case because the number of vehicles are much higher, is more than double from the previous case, so the emissions are much higher. But you can also see that the request served is also much higher, it's nearly about 100%. So the average passenger travel time has also gone down. It is now with public transport and DRT combined it's 77.7 minutes, whereas only public transport travel time is 90.6 minutes. So you can also see it is fruitful to take this PT plus DRT option rather than only public transport option. It is important. There are two notes that to be reminded, that the requests are very low because there are only 200 requests in 7 hour period. You remember we started from 8 a.m. in the morning to 2 p.m. in the afternoon. So with this 7 hour long window, only 200 requests were generated. So the vehicles had plenty of capacity available all the time. And we are also working on a better methodology for matching up request to public transport drop to that groups of different first mile and last mile requests. Now, the second problem that we are going to discuss is synchronization of public transport and traffic control. Now, this problem is very specific to urban case scenarios where, let's say, we optimize the traffic lights as well as line specific frequency or capacity of buses or public transport in a city. Now, other problems of this public transport and traffic control is the dependence of some public transport modes on traffic congestion and traffic control are highly uh, dependent. So, lack of flexibility means that there cannot be sudden changes between among the frequency of a particular bus line or traffic lights. The tangent approach is to for planned or unplanned event like failure of a metro line or something like that, the frequency and or the capacity of some public transport lines can be changed and the traffic controls for those particular intersection which are related to those lines can be also manipulated so that traffic operation can still be doing in a good way. The performance indicator that were considered in this study were user cost or affected PT lines, operational cost for public transport fleet, the congestion in some predefined areas like the most important area in the city or network, and reduction of system-wide emission. So this task was carried out for a small portion of network in the near to the Old Trafford Stadium of the Great Manchester City. So we have tested it with the Great Manchester Emerson model, which roughly has 10 public transport bus line to optimize and 24 signalized node. So in total, 81 phases were considered. So uh, I will okay, Laksha.
Yeah, you can continue like 2 more minutes.
Okay,
That's fine.
yeah. The thing is that I will open another window, so I will stop sharing this screen and I
Okay.
will share another window.
Okay.
Okay.
Yeah.
So this is the test network that we have used, and here are some markers like the KPIs that we discussed earlier, and this is the baseline scenario. Before optimization, before doing any optimization, and this is the tangent tool that we have developed for this kind of visualization and optimization task. So as you can see in the baseline scenario, what is the public transport frequency cost frequency, and it's like 60 minute one bus in every hour. The public transport delay is this, the operational cost is this, and congestion is like this, and the total emission is this. Now if we go to the optimized scenario, you can see how it is changed, and you can also please consider the color change in the network, and the meaning of them are also provided in the map legend, and these legends are based on the now we are considering mean delay time, which can be also shown in the delay time by the travel time as well as the vehicle flow. And in the left side you can see the resultant KPIs. So with comparing with the baseline scenario, the optimized scenario, the public transport frequency is improved, like it's from 60 minutes now it is 22.78 minutes. So every 22.79 minutes there is a bus for a specified lines. Previously it was 60 minutes, but the public transport cost delay has also gone up. The operational cost has de- the operational cost had deteriorated because now we are putting as we are putting more buses in the system, it has to be expensive than the previous case. But apart from that, all other KPIs has improved. The congestion has also reduced by 6.11%, and the emissions are also reduced by 9.62%. This is the optimized scenario, and the same can be seen for delay time based case where the baseline was like this and the optimized is this. and for vehicle flow also we can do the same. Now I will show another case study for public transport and traffic control. Sorry, DRT and mm, somehow it is not working, so I will resume sharing my screen. So as I have already shown, the for public transport and traffic control, the public transport cost for frequency has improved. The user cost has also improved, but the public transport operation, the only thing that deteriorated from the baseline was public transport operational cost. But that because we are putting some more buses in the system, so it is evident that the public transport operational cost will be higher. But how higher is it should be based on the stakeholders' input. For this preliminary study, we have put a minimal weight for the particular cost function, and we will improve that based on the stakeholders input and stakeholders need. So that's all. Any questions?
Thank you, Arka, for your wonderful presentation and the demonstration of the tool development, which is focusing on the optimization for the case studies. So yeah, for the webinar attendees, if you have any immediate questions regarding the presentation, you can go to the Q&A and you can write down your questions if you have any, uh, and then Arka can respond to those questions. And yeah, while we are waiting, just to carry forward the discussion, Arka, so considering you presented the synchronization of public transport and traffic control, and we see there's like an increase in public transport operational cost. Is there like a limit or threshold which you maybe came across or identified for uh, like public transport operation cost beyond which it will be difficult to implement the proposed solution? Or do you see any different cities which indicate differences in thresholds, if any, towards the operational costs?
Yes, the thing is that for this operational cost for this case has to be specified by the stakeholder itself. Like for now, we are having a static value for line specific cost, and then we are multiplying it by number of buses or number of public transport that we introduce for that particular line. For this
Hmm.
study, we didn't had any input from the stakeholder regarding this, but
Okay.
in the cost function that we have used, we have different weights for each of the KPIs. So based on how much the stakeholder wants to prioritize this operational cost, they can put their corresponding weight values so that by the optimization process, it will consider is much important or less important based on that. It based on the stakeholders input. But for now, for this study, we have not received any input from the stakeholders, so we have put a static value for each of the lines and then multiply it by how many buses are some things, some PT things are specified on that particular line. So there is a provision so that if the stakeholder wants to prioritize to optimize this operational cost rather than putting much weight on the travel time, it can
Mhm.
be done by changing or manipulating the weights.
Yeah, okay. Yeah, that's good to know. Uh, that, yeah, because I think definitely these optimization techniques will depend upon the variables which are identified and thresholds which different cities will identify. So
Yes,
for sure, it will uh,
it's
maybe make
completely
it.
depends upon the cities and their needs, what kind of things they want to
Yeah.
optimize. For now, we have decided for us like a demo purpose some weights and calculated this,
Okay.
and we also put the like we don't put this optimize operational cost much more priority, so this is the least priority for our
Okay.
optimization case. That's why it is increasing so much.
Okay.
But if we put some threshold, it will be not be increased that much, but other KPIs will be affected by that.
Okay. Yeah.
It's always a trade-off between.
Hmm. Yeah. There's always ups and downs in some different scenarios. But thank you for that feedback and a response to that question. I'll just check if there are any questions. And if there are no questions, but if attendees they still have any questions, you can still write it down, and we can always direct them back through future engagement opportunities, which I will share towards the end of the presentation. So you can always continue the discussion regarding traffic network optimization problems and the situation and solutions, which was currently presented by Arka. With that, I would thank you, Arka, for your
Thank you. Thank you
presentation
very.
and your time, and we will swiftly try to jump to the next presentation, which is development of arbitration models, which will be presented by Marius Gioroklis. And Marius, the stage is yours, so you can share your screen and yeah, perfect.
Thank you, Laxia, for the introduction.
Yeah. You can share your screen.
Yeah, happy.
Yeah.
Can you
Yeah.
see it?
Yeah, we can see it now.
Okay, great.
Thank you.
So, it has been quite interesting the conversation that you had before with Arka, that you have been saying repeatedly that there is a need to go and ask stakeholders what they need with respect to optimization, those optimization problems that we solve, and then we can use this opinion to let's say. Direct our work towards the desired direction. So this is exactly what we do with this consensus mechanism that is coupled with those optimization problems within Tangent. And what we do is we try to put this, let's say, personal touch into what we try to achieve. When I say personal, I mean obviously regarding stakeholders. So, as you know, transport network management is characterized by multiple stakeholders, different opinions on what should be done. Operators have very different needs than public ones, let's say the transit authority, and we also have multiple network configurations, from which we need to select the optimal one. Consensus-based decisions are difficult as it is. So within Tangent, we built a consensus building tool to respond to this issue. Arka just before has shown you some interesting results when we have applied those algorithms in Manchester in this instance. And for example, we have a very nice 63% increase decrease in frequency, which is good. So, but the question here is, from those let's say five objectives, what exactly which is the most important one? Which is the solution that gives, let's say, the performance in those areas that we need it the most? Is it public transport frequency? Is it congestion or emissions? This is something that should be elaborated before running those those optimization problems. So what we do is we try to achieve consensus on these performance indicators. To do so, we have asked ourselves, first of all, what is an opinion, which is intuitive, and when we try to model it. So we have selected this representation of pairwise preference relations, where we have solicited actual stakeholders, and they have given us their preference by evaluating pairs of objectives, which we have collected all in a matrix. This is more simple than it looks like. For example, you on the bottom left let's say side, you can see that, for example, in this table, that environmental performance is considered by this particular stakeholder to be slightly more important than service performance. Well, objectives, you can think of objectives, those KPIs that Arca has just told you about, service performance, network efficiency, which can be interpreted as congestion, environmental performance, which can be interpreted as emissions, and so on. And this 0.55 can also be linked to a linguistic interpretation, so that it is much easier for stakeholders to understand what they how to give this let's say evaluation. And the idea is that using this representation, we can derive objective weights. We can basically have a ranking of those network objectives, which then can be used to identify those optimization solutions that are much more interesting for our purposes. Having collected those opinions, we go ahead and we identify the most prominent opinions. We use it concretely to we use a fuzzy C-mean clustering algorithm to identify minority and majority opinion groups. So this is a very important step that helps us decomplexify a bit the problem, having it's much easier to work with two majority and minority opinions than 40 different opinions. And it also is very intuitive, because having those majority and minority opinion views is very important in order to understand what are the trending, let's say, opinions out there. Having The next step is to, let's say, understand how stakeholders communicate with one another. What we did there, it was to go and ask stakeholders to nominate some possible partners, and also provide some information on the nature of their interactions. For example, patterns of data exchange, the overall integrations of their organizations, and other indicators as such. And using a data-driven method, the Bayesian network, we were able to identify the probability for each stakeholder to communicate with other stakeholders of the same type, even if those, let's say, communication links do not exist as of now. And using this method, we were able to build a stakeholder graph, just a graph, imagine it like that, for each problem. For its problem, when I say problem, I mean when we need understand the communication patterns, when we need to apply a particular strategy, because you can understand that not all strategies are of interest for every stakeholder. So different stakeholder graphs can be expected for different strategies. Having both identified the important opinions and the stakeholder graph, we go ahead and we use RL in an opinion dynamic setting to simulate opinions exchanges between stakeholders. Quite shortly here, you can understand as an opinion game where each stakeholder expresses his or her opinion to another stakeholder. The initial stakeholder receives a feedback, and depending on whether this feedback is positive or negative, the initial position is either reinforced or decreased in importance. And obviously, also a stakeholder can also change his initial or her initial position to the other opinion. From the majority can shift to the minority opinion, and vice versa. No, this can be considered, the step that I have presented can be considered as, let's say, the communication table, where stakeholders come together and try to find the solution. But as we all know, this does not always lead to consensus due to divergent views. So in this case, we have also modeled an extra step, which is the step of an arbitration. where an arbitrator comes at this table, sits down, and goes there, identifies the two spokespeople, and then invites each spokespeople to each spokesperson to adjust their opinions in order to find consensus, but at the same time without getting too far from the initial points of view either. We have done this using this consensus reaching process framework, which is quite novel and interesting. And this is basically an optimization instance as well. Finally, we have identified after arbitration, obviously, we consider that the consensus has been done. The consensual opinion has been identified. You can consider it for the four optimization problems that we identify in tangent. These are the four consensual opinions. And if we use those matrices using some simple linear algebra to identify some objective weights on the importance, a ranking on the importance of the different things that are injected, let's say, of the different KPIs that we measure when applying those optimization frameworks. And we can trace this thing a little backwards and identify the correct network state that gives this performance, this optimal performance. A short conclusion, we create a decision support tool to facilitate decision making in this context. We aim at a realistic modeling of the usual steps of enriching decisions. This method is also data driven. We both stakeholder opinions and relations, the core inputs are actual input from stakeholders solicited within Tangent. Also a modular approach. Whichever module can be taken as is and be applied to a specific problem. For example, you consider that you just want to identify a minority majority opinions, you can just take the first one and apply it. And let's say to wrap it up, what we do is we provide the preference part in this preference-based optimization approach, which has been adopted within the work package 5, which deals with this problem. So that's all on my side. I hope you found it interesting.
Thank you, Marius, for your wonderful presentation on arbitration models. And similar, as I proceed, I'll proceed similarly to the previous presentation for the webinar attendees. If you have any questions regarding Mario's presentation, please go towards the Q&A column on top of the MS Teams, and there you can type in your questions, and Marius would try to attend those as soon as possible during the meeting. And okay, so while we are waiting for the questions, just to steer forward the discussion of the presentation. So considering the arbitration instead the Marius, there was an identification of true prominent opinions from different stakeholders. So do all stakeholders have equal weightage on the opinion? And if yes, then should there be a weightage be proposed which can match something like a real life scenario? And if yes, how can that sort of a weightage be proposed?
So that's a nice question. Indeed, all stakeholders are considered to have the same weights, meaning that as soon as we do collect an opinion, we do not weight it somehow. So yes, this is obviously not that realistic. Given that, for example, the approach to go in these issues as of now is that the authority who has, let's say, the legal power to change the system has this it's a top-down thing. They just decide, and maybe in some cases, in some cities, there is also consultation with other stakeholders, but usually the power holds in the agency that has the authority to change things in the network holds all the power in their hands. Um, I'm sorry, could you repeat? I think there was a follow-up there.
Yeah, as in
In
it was more like
the second part of
if
the
there's
question.
yeah, like approach of weightage being proposed. That was the second part.
So we're working on it. This would be the next step in this approach to maybe how understand how different power, the different power of different stakeholders can be integrated in this modeling.
Mhm. Oh, okay. Thank you so much. I think we look forward to that those updates, and for probably in the next webinar in the series, that can be a platform to address that as well. Let me just check if there are any other additional questions yet. Or no, or we still have time, so just I can try to squeeze in a short question. Considering the approach like you of adjusting opinions, uh, is there consideration considering there are like 4 network objectives in the presentation for tangent? It was surface performance, network efficiency, economic performances, and environmental performances. So is there a quantitative limit to address additional objectives when identified?
So that's a nice question as well. We can also, you remember that we had 4 objectives. What we can do is we could add more. The problem is that if you remember this table, as soon as you add objectives, given that the objectives are evaluated in a pairwise fashion from stakeholders, for example, if you have 2 objectives, objective A and objective B, you will have those pairs. What is your evaluation in of the objective A versus objective B for all of the objectives A and B? So what the problem here is that by adding objectives after, we have found that after 4 objectives, the burden for stakeholders, which are already difficult to find and have them respond to questionnaires, gets quite high without much additional value for us. So we think that, let's say, 4 objectives are the sweet spot in those works.
Okay, I think so like 4 objectives are like a sweet spot for getting the arbitration done in a realistic manner, I believe.
Mm-hmm.
Yeah. Okay. Thank you so much for that opinion and the feedback on the discussion. And for the webinar attendees, for sure, if you have any, if something pops up from even later after the webinar, you can still carry forward the discussion, and I can share. You can do it how, but before that, what I'll do is I'll proceed forward to the second poll for the presentation. This is considering the future plans for the webinar series in Tangent. So if you can see your screen, uh, the last webinar in the series will give more of an in-depth overview of the tool, which was sort of in a demo. It was displayed uh, by Arca, but it will be further developed and within Tangent project through the case study implementation in the 4 cities which I had previously shared, which is in Rennes, Lisbon, Manchester, and Athens. And considering the webinar series, we have already executed 3 webinars, including this one, which is the 3rd webinar. And there will be a tentative date for the webinar 4 around August, depending upon the development of the tool. And the focus will be on the integrated tool for cooperative traffic management and results of the implementation, case study implementations. And considering the fourth webinar, which is in the series, I would like to draw your attention to the second poll at the Mentimeter. So what I'll do is I'll share again the screen for you. If you can see, yeah, if you can see your screen, there should be again the same Mentimeter code. So basically waiting for your prompt. So if you can see that screen, just give a thumbs up and I will proceed towards the next, towards the final poll of the presentation. The code is the same, menti.com at 23190755. So if you're there, I'll slowly, perfect, and we are getting some likes. So I'll quickly shift to the second part of the poll. So the question is, what are the topics you would like to see covered in the next Tangent webinar? So basically, considering in today's we focused on optimization and arbitration models, and the final webinar will focus on the tool development and the case study implementation in Tangent. So what aspects of the presentations would you like to see, considering the topic is on the tool and the case study implementation? Okay, we see impacts of MTM. Okay, I believe MTM stands for multimodal traffic management, if I'm not wrong. So what are the impacts? So considering a multimodal traffic aspect, which include active modes, public transport, private modes, and maybe also depending upon different infrastructures. It's just not only the road, but maybe water, depending upon the diversity of the modes. So, okay, that can be one aspect to look into. And if there are any further topics, we are still live on the poll. Traffic forecasting. Okay, so yeah, traffic forecasting. Yeah, we had a webinar before this one, which was focusing on traffic forecasting, which was presented by IMSUN and IMEC. But those resources are still available with us if you want to go in depth on the traffic forecasting aspect. But those tools, the implementation of or findings of those presentations and how they are used in the case study implementation will definitely be taken into consideration. Third point is how much optimization can be done in a daily basis for public transport and demand responsive transport, considering daily dynamic synchronization. Okay. Yeah. Thank you for these opinions. Oh, there's one more, practical cases and how it works on the ground. Yeah, I think that's more important for the final webinar where it will be focusing, considering it will be, at least for the 3, it's on site, and for the Athens case study, it's more virtual approach in Tangent. So seeing practical cases and how it works on ground will definitely be and then more enlightening, considering how different approaches, physical and virtual approaches, are carried forward. Okay. So keeping those points in mind, I will. These responses will be utilized for the future upcoming webinar. And going back to the final part of the presentation, where I'll share how you can still be a part of Tangent. So we have this platform of Tangent Forum through Mobility Academy, where it aims to coordinate engagement of external stakeholders and experts. And here we provide framework for continuous engagement through this Mobility Academy, where the progress, news, and recordings of previous events, even minutes and ongoing developments in Tangent are shared through discussion, are also discussed via discussion forums. So here, if you have any additional questions or things you would like to share, or even ask the speakers from these presentation, or even from the previous presentations, you can always use discussion forums to generate these engagement activities and for knowledge exchange. So good part is that it's free. The Mobility Academy, the access to webinar and related materials, so you can always access them, and also the discussion forum and the information on the case studies. So these are continuously being updated. So by the end of this week, at least you will have the revised user interface for the first three webinars and the information related to it. At least for the first two, it's there. For the third one, depending upon when the materials are developed, they will be uploaded soon. And this is just how it looks like for the discussion forums, where you can log into that. But for that, let me just share the information, which will be useful for people who have not yet joined the webinar. Sorry, the Mobility Academy. So if you see in the chat, let me just share the information. Okay. Yeah. So if you see in the chat, you have this information about the Mobility Academy and my email, but also the website. So if you want to have access to Tangent Forum, so just write me an email, and I will, based on the added information that will be provided, then you can get in touch and you can continue and also respond to certain questions which are already ongoing in the discussion forum. And I think that will be it.